Well, hello guys, and welcome to Mr. G Physics. We're going to be doing another stream for the grade 11 and grade 12 again. This one is going to be related to vectors, but these vectors are going to be in equilibrium. So we're going to be working with forces in equilibrium, and that is very important for grade 12 because in actual fact, this one is going to be in Newton's first law. So we are dealing, in other words, with Newton's first law. So we're going to do two questions. They won't be that long, but we're going to look at some mistakes that learners make when they're doing this question and some changes that came from lately, and they won't give marks any longer, but they gave mark last year. So it's a very important part of the work. There's the two questions, but before we go to the two questions, I want to speak about something important. So let's have a look at some revision, just for control before we start answering any question. First of all, it's equilibrium. So let's go and write equilibrium. Now, equilibrium. What does equilibrium mean? And this one is very important. Very, very important. Equilibrium means that the F net is equal to 0. It doesn't mean that there is no forces. It means that the net force is equal to 0. Now, if the net forces is equal to 0, that means that the resultant forces, let's say R in Y, is equal to 0, and R in X is also equal to 0. That is the meaning of equilibrium. All right, now, important here also, when this one happens, when an object is going to be in equilibrium, when the net force is equal to 0, when is that going to happen? There are two scenarios. Scenario number one is the velocity is equal to 0. Object does not move. The object is at rest. So if the object is at rest, it means it's not moving, then the net force is equal to 0. And then, of course, the forces are compensated. All right? The second scenario is when there is velocity, but the velocity is constant. All right, so those are the two scenarios when the object is at equilibrium and therefore the net force is equal to 0. Scenario one is when the velocity is 0, object is not moving at all, like for instance, object that is hanging, like this traffic light. The traffic light is an equilibrium, the object is not moving. So the net forces acting on that traffic light is 0. All right? And the second scenario is when the object is moving, but it's moving at constant velocity. That is the second scenario. Guys, this one, in other words, and that one is for later on, it's not for now, that is for later on. This is what we call Newton first law. Newton's first law, you will learn eventually the right way of taking Newton's first law, but in other words, it says that if the net force is equal to 0, the object is going to be at rest or not moving, or is going to be moving at constant velocity. In other words, saying it from back to front, if the velocity of an object is equal to 0, or the velocity is constant, it means that the net force is equal to 0. There was no net force. All right, so this one is important before we start working because there is another important thing to know. Now, and that one is now straight for the question we're going to solve. If the net force is equal to 0, the resultant in Y is equal to 0, and the resultant in X is equal to 0. What is the meaning of resultant in, oh my goodness, my pen. What is the meaning of resultant in X is equal to 0? It means that, right, let me write it here on top. I hope we can see properly. Right is equal to left. And we are referring to the axis. All the forces that are acting on the left and right side are equal because the object is in equilibrium. And this one is important for the work we're going to solve just now. What it means that the resultant in the y axis is equal to 0, it means that up is equal to down. Now, what I mean down in the axis. from the origin. So this one is the equilibrium. I think if you know this little summary, then you will be able to answer the question without any problem. This is a summary. I'm going to repeat once more. It's not hard for this one. Equilibrium, net force is equal to 0. If the net forces is equal to 0, it means that the resultant forces in y is equal to 0 and the resultant forces in x is equal to 0. What does it mean? It means that all the addition of all the forces on the right side of the axis is equal to the addition of all the forces on the left side of the axis. And then in the y-axis, what does it mean? The addition of all the forces that are on top of the axis is equal to the addition of all the forces down in the axis. And this one, guys, is in other words, Newton's first law. So now how do we know that an object is in equilibrium? Because the object is either not moving or it is moving, but with constant velocity. And that's only what we call Newton's first law. So this is like a summary to begin. Now I think we are like ready to start with the question. I'm looking for my pen. Which one would be the best one? Yeah, I have to organize my pens. So that is the summary. You can take a screenshot or whatever you want. Let's move this one here and let's begin with the question. Now this question, in this question, we have a traffic light. We're going to read the question in a second. I'm just going to do the drawing. We have a traffic light. Let's draw a traffic light like this, for instance. It doesn't matter. And then there is a rope holding the traffic light in that direction, and there's a rope holding the traffic light in that direction. And this one is not accurate drawing. This one is a rough drawing. We don't have to be accurate here, but just for you to know what is happening. So there we go. That is the drawing. The traffic light is in that direction. Here we have an angle that is 40 degrees, I believe. We're going to check, and this one is 30 degrees. We're going to check now. This one is the traffic light. Okay, so let's go to the question. Read the question and start answering the question. Okay, the question is here. The question says, a traffic light of mass 20 kilograms hangs at rest. If it's at rest, it means it's at equilibrium. So all the summary we just looked at is applicable here. Top is equal to bottom, right is equal to left. Okay. Rest from two cables attached to the horizontal. The cables make an angle of 30 and 45 degrees. I was waiting for that 45 so I can fix it here. I thought it's 40. There we go. With the horizontal. And then you can see the picture. The first one is draw a label free body diagram of the traffic light. Now, free body diagram, you're going to learn eventually in details when you do Newton's law, but we can introduce it now and we can speak about the mistake or something that we did last year. It was right, you get marks, but you are not getting marks any longer. All right, so let's go to free body diagram. Now, what is the free body? This one is not the free body diagram. This one is a picture with the angles, the tension. It's not accurate, it's not important. Now, a free body diagram is the drawing in which the object will become a dot. So we don't have objects here, but we have a dot. And all the forces are going to be pointing out of that specific dot. This one is what we call a free body diagram. All right, so all the forces acting on that traffic light will become out of the dot. What forces are acting there? Look there in the picture, in the actual one. We have a rope that is going to the top right, and the other one is going to the top left. Those are the rope. Those are the forces acting here. T1 and T2, or whatever name you want to give them in here. Okay? There we go. Let's go to the question here now. The free body diagram, what forces we have? We have a T1 that is acting in that direction. Let's call it T1. We do not include the angles here. You don't have to include the angles for the free body diagram. And we have here another one. Let's make it a little bit down to be more accurate. But remember, this is not, or it does not need to be accurate in terms of length of the vector. All right. So here we go. There. This one is T2. 2. That is the first two forces. Now, there is another force, which is the weight pulling the traffic light down. That weight is pulling down the traffic light. I'm going to draw it here. There we go. And this one is the weight. Now, for control also, weight is equal to the product of mass and acceleration due to gravity. We are going to do this one later on. This one is W is equal to mg. And g is equal to 9,8 meters per second squared. All right. So this here is the free body diagram. Now, what is the mistake that last year we got marks, but not this year? This year they are not giving marks any longer for that. And it's the component. In this drawing, you cannot add components or you will not get marks. You will lose the marks. Last year, previously, they accept to draw components instead of forces, but this year you cannot do it anymore. You only have to draw the forces. Without component, do not add axes, do not add anything else. This one is the free body diagram that they ask you to calculate. All right, and I hope that one is quite clear. That one is in terms of the free body diagram. So that one is the one. That one is the one. Free body diagram, no components, no angles, nothing. That is the first question. When you do that, you will get 1 mark per force. Here, in this question, I did not include the marking, the number of marks, because it's not the purpose of the stream, but you have to look always that one there. All right? Because it is important. It is very, very, very important. So I don't know if there is a question you can ask, otherwise we continue. We continue there. So that one is in terms of the free body diagram. Now, the next question, they say calculate the tension in each cable. We have to calculate the tension in each of the cables, and the data we have is the angles, but we also have the angles, but we also have the mass of the two objects in here. Okay? Let me just look in here. So we have to use this one here. We have to use this specific summary. Let me see where it is here. Oh. We're going to use this summary. You have to remember that top is equal to bottom and right is equal to left. Top equal to bottom, right equal to left. A traffic light of mass 20 kg hang at rest from 2 cables attached to horizontal support. The cable makes angle of 30 and 45 degrees with the horizontal. Draw the label free body diagram. We already done it. And now calculate the tension in each cable. Now, instead, we're going to go this part here. This summary is important. Top is equal to bottom, right is equal to left. So we're going to go here and let's start answering. Look at that. Look at that. Let's start answering that specific question, but we need a free body diagram with components. We cannot use this one because we lose marks if we draw components. So we're going to redraw, but this time we're going to add components. All right. So we're going to go here. I'm sorry about, I don't know what happened there. I have some issues with the quality. I got some messages there with the quality. Okay. So let's go here and let's do this. We're going to do it again, but this time I am going to add the component. Note, this one is for the second question. This one is for question 1.2 and not for question 1.1. So in this case, I can draw the components, okay? So there we go. I'm going to draw here the other force. This one is T1, this one is T2, and then I have the weight down. But I am going to draw the components this time. I need it because otherwise I might get confused. So in this case, we're going to break T1. Then we go into components there, like that. And we have here, this is T1 in X. The angle they gave us is this one, which is 45 degrees. All right. And then this one is adjacent. The X component is adjacent to the angle. So this one is going to be equal to T1 multiplied by cos of 45 degrees. The same we're going to do for the other vector. We have that, and this question is a little bit tricky. We're going to have the component here down, tuk, and then we have here the x. This one is t2 in x, and t2 in x is equal to t2 multiplied by cosine of theta. Let me just fix it there, the word cosine of theta, because it is also adjacent to the 30 degree here. Cos theta. All right. So now here, we don't have values. We don't have values. This question is tricky. We don't have values, but we know, because it's at equilibrium, and we mentioned that one when we started, that this side, right, is equal to left. So we don't have value, but we know that one is equal to the other one. All right, and that is very important for the work, because we don't have any value here. This question is with no values at all. So we know that T1 in x is equal to T2 in x. Why that so? Because the system is at equilibrium. Okay. Now, without numbers, because we don't have numbers, we have only the equations. I am going to substitute each equation in here. So I have the T1 in x is T1 multiplied by cos of 45 degree, and that is equal to T2 in x, which is T2 cos of 30 degree. There we go. They are equal because it is at equilibrium. Right is equal to left. That is what we are doing here, but we don't have values. So the only thing is we stop there. We don't have value. We don't have value. Now, if you want, you can now rearrange for one of the two t's. And that is what we are going to do. So we're going to say that T1 here, and this one is mathematics, okay, is equal to T2 cos of 30 degrees divided by, this one is T1, divided by cos of 45 degrees. And then this one, we're going to leave it as equation 1 so we can substitute in the next work. All right, so this one is for the x-axis. I'm going to go again through the x-axis. We have here that I broke the T1 and the T2 into two components. All right, x component. There we go. Because the system is at equilibrium, Tx on the right side is equal to Tx on the left side. T1 in x is equal to T2 in x. That is what we have here. So I substitute in here, and we get that T1 is going to be equal to T2 cosine of 30 degrees divided by cosine of 45 degrees. That is what we have, okay? But we don't have enough data. So we have to stop there. Let me use the other board. I am going to erase this one because I need the space. Now we have to go to the y-axis. Now we have to do the same work, but for the y-axis. Let me see this. Which one color I can use? I can use this one. So let's do the same, but for the y-axis. All right. Now, what do we have in the y-axis? Let's break here into components, and then we move there. What do we have into the y-axis? T1 is going to be broken into T1 in y, which is this one here. And that one is opposite side. This one here is T1. Let me just note like F. We keep T. T stands for tension, and later on, another time, we'll learn about tension. T1 is equal to T1 in y, is equal to T1 sine theta, which is 45 degrees, because it's opposite to the angle. And if we do it on this side here, for the other one is the same. We break it here, and we have that this one here is going to be T2 in y-axis, and it's also opposite. So this one will be equal to T2 multiplied by sine of 30 degrees. Okay, that is what we have there. So now, let's go back to the part of equilibrium. It is an equilibrium. So everything on top is equal to everything at the bottom. On top, we have two forces, and W is equal to mg. We're going to speak about this one now. We need it. We need it. So top we have two forces, at the bottom we have one. Let's go here to do the y-axis here. So what do we have for the y-axis? We have that T1 in y plus T2 in y is equal to W, which is at the bottom. All this one is on top. I'm going to do this for you. This one is top. This one is down. Top is equal to down. And that is what we actually say. All right. So now we have to substitute. We have to substitute for each of them. So what do we have? T1 in y is T1 multiplied by sine of 45 degree plus T2 in y is T2 multiplied by sine of 45 degree. And all this one is equal to W, which in actual fact is mg. We have now all that equation there. But we don't have, we have two unknown. We have two unknown because we don't know T1, we don't know T2. We don't know any of those. But in the previous work, when we went to the x-axis, we say that T1 is equal to this one. So we can substitute this one in the other equation. We can substitute that one in the other equation, which is what I'm going to do now. T1 is there, so I'm going to substitute here, guys. I hope you're following me. T1 is T2 cos 30 degree divided by cos 45 degree plus T2 sine 45 degree equal to the mesh, which is 20, I believe. It's 20. 20 multiplied by 9,8. And then now we can calculate T2. Now we can calculate T2. If you want, you may use your calculator to break this cos and sines and things like that. It will be better to do calculation. And in actual fact, we're going to do that. And let me get my calculator. Let me see quickly here. We have that is cos 30 divided by cos 45. We get that this one is 1,2247. So I'm going to round off to 3 decimal places. So this one is 1,225 T2 plus, and then I'm going to do the same here. Sine 45, I'm going to work with decimal numbers, and that one will give me 0, plus 0,707. T2 is equal to, and this is 20 times 9,8, 196. There we go. Okay? I hope you are with me. So now here you just have to add. This one is common factor, and you rearrange. And then we are almost done with the calculation of T2. So here, we're going to calculate that one real fast. Now it's 1,225 plus 0,707. There we go. And that is 1,932. When you substitute here, you get that this one is 1,932 T2. We calculate in T2 first, all right? We calculate in T2 first. T2 equal to 196. You rearrange, you get that T is equal to 196 divided by 1,932. Let me see how much we get. Is 196 divided by answer. We get 101. T2 is equal to 101,45 Newton. That was T2. It's a lot of work. The question is more difficult than I thought. It's more work than I thought. I thought it's easier, but it's actually tricky. And that is T2. Now, how do we get T1? T1, we have to go back to this equation. There we go. We have to go back to that equation, which we are going to do real fast here. And then that is how we calculate T1. So let's calculate T1 with my pen here. All we have to do is to substitute here. We have T2, we calculated, we substituted in there. All right? These the values. I'm going to move this one here so you can see it properly. And so there we go. Let me put this one here. We have the T1 is equal to T2, which is 101,45 multiplied by cosine of 30 degree divided by cosine of 45 degree. You substitute, let me have some water quickly. You substitute in there, in the calculator, let me use the calculator quickly. We have that is 101,45 cos 30 divided by cos 45. There we go. 124,25, and that is T1. T1 is equal to 124,25. That is how we calculate both T's. It is tricky. The question is tricky. You can look. I can go back and start over because it is difficult. So let me start over what we done. Okay. So let's go through the work real fast. We broke the two vectors, the two tensions into components, X and Y. All right. Remember, the system is at equilibrium because it's not moving. So we broke into X and Y. You need to know that on the X-axis is at equilibrium as well. It means that everything on the right, which is T1 in X, will be equal to the left, which is T2 in X. All right. And that is what I did here. T1 is equal to T2. Now, if you go here, the T in X, the tension on the X-axis is going to be the adjacent side and is therefore multiplied by the cosine of the angle, which is 45, and here is 30 degrees. Okay, so here, that is what I did. I came here and I say T1 in X is equal to T2 in X. They are equal, but we don't have values. So I'm going to substitute just the formulas. T1 in X is T1 cos of 45. T2 in X is T2 cos of 30. We don't have values, so we have to work like this. Then I rearrange to calculate either of the two. In this case, I select T1. It doesn't matter. So if you rearrange, you have the T1 is equal to T2 cos 30 divided by cosine of 45. I move the cosine of 45 to the other side. So we have here now a formula or an equation for tension 1. Okay? Now, that is on the X-axis. We cannot do nothing else. We have two unknowns. Let's go to the Y. So in the Y, before I use this board, on the Y, we have that everything on top must be equal to everything at the bottom. So the components on the Y-axis is equal to weight, which is pointing down. And weight is equal to mg. We spoke about that one already. Okay, so then is when I came to my other board and I worked for the Y-axis. And I said in the Y-axis, T1 in Y plus T2 in Y is equal to W, which is at the bottom. Top is equal to bottom or down. All right. So I substitute. Now the components, there is opposite side to the angle. That is why it's sine 45 and sine, I use 45 here, but it's 30. T1 is 45, T2 is 30 degrees. I think I make a mistake with the numbers here. This one is 30 degrees, too many times here. Here is T2 is 30. I make a mistake here. I make a mistake there with the numbers, but that is not a big issue here. This is 30 degrees. Okay? 30 degrees. So you can do the whole calculation and the difference won't be that big. But that is the one. So then you calculate T2, which is here, and you substitute in T1, and then is how you calculate both tensions. I hope that one is clear. The question is not that easy as I thought it was. Okay? I hope it's clear. I think we can go look the next question. you have any question, you are welcome to ask. If you have any question, you are more than welcome to ask. Okay, let's go to the next question. Next question is this one here. Let's look at that specific question there. Okay, the question says a metal ball of weight W is suspended by two ropes fixed to the wall and the ceiling. As the figure, you can see the figure there, the picture there. The tension in the rope is T1 and T2. Tension T2 is 80. Now, this case is easier. They are giving you one of the two tensions. They're giving you one of the two tensions. Draw a force diagram to represent this scenario. My camera is there at the back. Let me move it up a little bit. Represent this scenario in terms of three forces in equilibrium. This is not the free body diagram. Let me erase it here. They ask you to do a closed triangle, and let's do that. Let's do the closed triangle because the system is at equilibrium. The triangle you're going to draw must be closed. Okay, so that is the thing. So let's do the drawing that they want. And for this drawing, like free body diagram, values are not required. You only have to be able to draw the forces in the triangle. So let's do that quickly. If we come here, and we draw the first force, which is, look at the direction there, right? First force is going in this direction. That is T1. The second force, starting from the head, is going in that direction. Remember, it does not need to be accurate. This one is T2. And then the last one must be close straight down, which is actually weight. This one is the triangle they want you to draw. It is a closed vector diagram. It means the head of the last vector, it will end on the tail of the first vector you draw. And that one is the closed vector diagram that they want you to draw in the question. They don't ask for free body diagram. This one is a vector diagram to show that it's in equilibrium. Now, you have to draw the free body diagram if you have, which is not the case, but let's do it anyway. If you have to draw it, then remember, starting from a point, and you keep the forces going away from there. This one is T1, T2 is in this direction, nothing need to be accurate here. This one is T2, and then the last one is the weight, which is pointing down. This one is weight. Those are the three forces for a free body diagram, not for a triangle they ask. The triangle they ask is that one there. This one is question 2.1, that triangle. Know this. Okay? But this one we need it for the calculation. We need it for the calculation. So let's go and look at the question. The next one. The next one, where are we? Here we go. Let me just look for it. Sorry. Here we go. Determine by calculation the tension T1. So we have to calculate T1. Now this one is much easier. This question is much easier than the one before because we already know one of the tension. They say tension 2 is 8 Newton. All right? And you're looking for one. Let's go here and let's work with the angles in the drawing. All right? So what do we have? And let me just do it here so I can show you. What do we have? First of all, this is the drawing. I'm going to use the same diagram here. I'm going to draw the axis, and I want you to note in the picture, if you look carefully, the 60 degree to the ceiling, that 60 degree is here. This one is 60 degree. All right, that one is important. But now here, for the y-axis, for the other T2, then it's the wall, which in actual fact will be the y-axis. Let me do the axis quickly so you know what I'm talking about. The angle they're giving you now is this one here. That angle is the one that is 80 degree. 80 degree. And that's it. From here, it's very simple. Now you need to know, be careful with the angles and note if the axis is either the adjacent or the opposite. Okay, now what we have the T2, and I'm going to write the data there. I'm going to fix this one here and write the data there so we can use it. T2 is equal to, is given to us. Let's quickly look where it is. It is 80 Newton. This one is 80 Newton. We need that one. Okay? So now how we calculate T1? Remember, it's at equilibrium. We're going to break these vectors into components in the x-axis as well as in the y-axis for later on. Okay? So let's start with the x. This one will come down and you will have here T1 in x. In this case, this side is adjacent and therefore it's going to be T1 multiplied by cos of theta, which is 60 degrees. But here, in this case, is opposite because the angle is there. So this one, in this case, is T2 in x, is going to be T2 sine because it's opposite to the angle. As you can see there, it's opposite to the angle, okay? So I hope that one is clear. This is cos, but this one is sine. Why so? Because of the angle, the position of the angle we're dealing with. So now, we're going back to the equilibrium part when we started the stream. Right is equal to left. Right is equal to left. What do we have on the right? We have that T1 in x is equal to T2 in x. All right? How do we calculate T1 in x? T1 cosine of 60 degrees. So this one is T1, which is actually what we are looking for, multiplied by cosine of 60 degrees. What is T2 in x? T2, which we know, multiplied by sine of 80 degrees. Let's make sure it's 80 degrees. Always re-look at the question. If you don't remember like me, it's 80 degrees, yes. And then you substitute numbers. T1 multiplied by cos of 60 degrees is equal to T2, which we know is 80 Newton, multiplied by sine of 80 degrees. T1 is equal to 80 sine 80 degrees divided by cosine 60 degrees. And then you get the answer there, which we are going to calculate real fast. My calculator, where I place it, is this. So let's do it quickly. This one is 80 sine 80. Yes. Divided by cos 60. And then we get that T1 is equal to 100. This one is equal to 157,57 Newton. T1 is being calculated. I hope you understand. If you have any question, you may ask. Let me just try to get the other little board and clean it because I need it for the next question. So long, you can ask questions if you have any. This topic is problematic. It could be difficult, and in the test, you are going to have 1 or 2 questions on this topic, okay? 1 or 2 questions will be for this topic, and it could be difficult. It could be really difficult. Okay. So now, the next question say, determine by calculation W, and that is the end of the question. Now, how are we going to determine W? Guys, you need to remember that W is on the y-axis. Look here. W is on the y-axis. So we have to work on the y-axis. To do that, we have to break the two forces into the y components, which we didn't do before. We're going to break into the y components. Let me go here. You break this one. Tuk, 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 tuk. Is here. Then we have T1 in y. And if you break it here, you have T2 in y. All right. T1 in y is sine, but T2 in y, you can see, is next to the angle, is adjacent. Okay. And now we're going to use the rule of equilibrium. So what we have here for rule of equilibrium? What do we have here? We have that T1 in y plus T2 in y is equal to W. This one is extremely important for Newton's law later on when you work with forces that have angles. You have to do this one to calculate the normal or any other force that you will deal with. So now here T1, remember, is sine. So it's T1 sine of theta, which is 60 degrees, and then T2 is cos because it's adjacent. T2, let me write the 2 there, that's not the 2, that looks like something else. This is T2 cos 80 degree equal to W. Guys, the rest is substitute. You have all the values here. T1 is being calculated is 157,57 multiplied by sine 60 degree plus T2 is given is 80 cos 80 degree, and that is going to be equal to W. When you substitute, which I'm going to do real fast, we have, let me see, 157,57 sine 60 plus 80 cos 80, that will be equal to 150,35. I got the W is equal to 150,35 Newton. There we go. Guys, that is the end of the question, if I'm not mistaken. Yes, it is. There we go. I hope it helped. I hope it helped. It's difficult. The first question is difficult and tough and problematic, but it's a good question. It's a good question for a test. So, I don't know. I hope it helped. You can now ask any question if you want to know something about this topic. I will answer. I will wait like 5-10 minutes for you to ask any question you may have the topic. Otherwise, we can. You can tell me topic is difficult. I hope it helped. I hope it helped. Next stream maybe is going to be on Newton's law. You're supposed to start this week with Newton's law already. And Newton's law, you need this one for Newton's law. If you don't know this one, in actual fact, we say this one is Newton's first law. Okay, this is Newton's first law. This question, the first question we did, this one here is a very good question. It's difficult. You manage to do that question, then everything will be short. It won't be, I think, a question more difficult than that one for you guys. But any question that you could have, any problem? I'm sorry about starting. I had some problems. I received a message from the program I'm using, and then the stream also was about to stop. Make me a little bit nervous at starting. If it's no question, then we'll stop. You can ask questions. Okay, thank you guys. We're going to stop, and then I'll see you next Saturday, I hope. Thanks a lot. Much love to you all.